Alright, so in this video, I'm going to be explaining another important article with the title, Can a strong structural encoding reduce the importance of message passing? This ICML paper in 2023. The most prevalent class of neural networks operating on graphs are message passing neural networks in which the representation of node is updated iteratively by aggregating information in the one hop neighborhood. Since this paradigm for computing node embedding may prevent the model from learning coarse topological structures, the initial features are often augmented with the structural information of the graph, typically in the form of Laplacian eigenvectors or random walk transition probabilities. So in this work, we explore the contribution of message passing when strong structural encoding are provided. We introduce a novel way of modeling the interaction between feature and structural information based on their tensor product rather than the standard concatenation. So it's a tensor product of feature and the structural information, not just concatenation. The choice of interaction is compared in common scenarios and in settings where the capacity of the message passing layer is severely reduced and ultimately the message passing phase is removed altogether. Our results indicate that using tensor-based encodings is always at least on par with the concatenation-based encoding, and that it makes the model much more robust when the message passing layers are removed, and some tasks incurring almost to no drop in performance. So you know about message passing neural networks that any graph neural network can be encoded like this. We have aggregation and update. And now an established paradigm to frame the expressive power of GNNs is the graph isomorphism test. A different approach amounts to augmenting standard message passing neural network formulation in various ways by incorporating topological information from the underlying graph. In accordance with the conventional, we use the terminology structural features or structural encodings. Such augmentation can take many forms, and we outline two broad strategies. One way considers the graph's structure as explicit features. By considering rings as explicit features to be learned, we construct more complex neighborhood structures with the consequence of being able to distinguish strictly more graph isomorphism. And a second approach is to include structural information in the node features, meaning that the initial feature and structural information are altered as follows, where P is just the structural information of node I. Typically, the encodings are formed by first concatenating H sub I and P sub I, and then passing the resulting states through an MLP. Augmenting node features with graph-aware structural information can be particularly useful for graph transformers, where structural information is used as positional information when pathing messages. Although different strategies for augmenting features with graph information have been proposed, random walk transition probabilities and Laplacian eigenvectors constitute the most adopted class of structural encodings. So we have a transition matrix R, and R is raised to the powers to find structural information for random walks. A is the adjacency. An alternative to using random walk features is found in spectral graph theory, for example, the study of properties of graphs using eigenvectors. I have a playlist for spectral graph theory, so we can skip this talk. Now, the main idea is using tensor product structural encoding. The tensor product between matrices A and B is just is a matrix formed by replacing each element in A with the product of that element with B. This is the tensor product of A and B. Therefore, when considering a tensor product B for vectors A and B, we find that the product is the element in the index, being vector found by concatenating vectors B scaled for each element in A. Typically, when constructing an encoding for our input features and structural information, the respective vectors are first concatenated and then projected. So for some weights W, to embed the input features using tensor product, we simply mimic this approach. Because not only we need the features, but also we need the structural information. So the tensor product of them times the weight is a good encoder. However, notice that the number of inputs to the projection has increased significantly, which is something we account for in experiments by significantly reducing the input dimension. It is common for a message passing layer to update the feature of a state by using a linear projection of the current state combined with the aggregation of the messages from its neighbors, followed by a nonlinear activation. For many common instances, the MPNN layer operation can be taken to be an MLP. Suppose that H sub I for some D, as in the cases of D-dimensional features, augmented with D-dimensional structural encoding using a tensor product. We can then reshape H sub I to be a D by D matrix, which we denote by mat of H sub I. We then propose to approximate the linear projection with a series of small matrices, this Q and W, by left and right multiplying with mat. The update is then used on the current state and the aggregation over one hop as per one before the action of a pointwise nonlinear activation. So we note that if the node state satisfies this tensor product, then reshaping the tensor product state into a matrix simply corresponds to writing it as the outer product, meaning that the sparse layer update takes this form. To ensure models considered can embed the structural information well, the input features and the structural information are first embedded separately before their concatenation. So this is embedded separately, this is separately, and then we have this concatenation. So we report the final training and test performance over 3 runs. We use these structural encodings. And for example, the diagonal entries of random walk matrix R with random walks up to length 20. They did it for peptides because it's good for long-range graph data sets. So over 3 runs with different seeds, we can have for different architectures like graph convolution, graph isomorphism network, and graph sage that I explained. Graph sage in the previous video, I explained graph sage. So is the choice of geometric encoding important? The result obtained on zinc as well as those on peptides would highlight that when using the full message passing layer, it seems that there is no significant difference in terms of performance between either of the two, despite the two approaches being geometrically very different. This brings up the question of what the message passing is actually learning based on the structural information, and to what extent the message passing layer is actually needed. Our investigation supports the idea that the tensor product encoding is significantly more resilient to the reduction of the number of parameters in the message passing neural network, or in fact the removal of the message passing neural network altogether, in contrast to the concatenation approach, where instead eliminating the message passing leads to serious performance degradation. So, conclusion. Our results indicate that when no message passing neural network layers are included, tensor encodings are able to better learn on graphs in general, and even able to perform on par with models with message passing neural network layers in some tasks.